Good evening, everyone. My name is Brian Hoskins. I'm chair of the Grantham Institute at Imperial, and it's my great pleasure to welcome you to this inaugural lecture of Professor Tina van der Flierdt. So Tina came to this university in 2008, and she'd done her diploma in Bonn and her PhD in ETH Zurich, and then some research positions in Columbia in the USA. And so she came and she went through the ranks here as a reader 2014 and professor in 2017. Now, why am I here? Well, I'm not a member of the department. I was actually the first director of the Grantham Institute for Climate Change, and I came almost the same time as Tina did to Imperial. And being the first director of this Climate Change Institute, I was looking around for enthusiastic young lecturers doing interesting things relevant to climate change. And there was no doubt that Tina ticked the bill in all ways. She certainly was enthusiastic, and the topic she was on was hugely important, I thought, because there's a lot of discussion of sea level rise with climate change, and then people looking at Greenland and thinking, well, could that be destabilized? West Antarctic ice sheet. But the big amount of ice is there in the East Greenland. And the question is, could that be destabilized, or some of it be destabilized in future, when the sort of 1 meter sea level rise that the IPCC talks about may be a real underestimate, or certainly within a few hundred years. So that was the topic, and Tina was doing very interesting work on that, and it gives me great pleasure to see how she's succeeded Imperial over the years. And it will give me great pleasure, too, tonight to hear Tina give her lecture, Drilling for Our Future in Antarctica's Past. Tina.
Thanks, Brian, for your kind opening words, and thanks everybody for coming tonight to my lecture. I want to start you with a beautiful view on the Eastern Arctic ice sheet taken from one of the expeditions I went on. And I want to really start with acknowledging some people without whom I couldn't be standing here on this stage. I'm co-leading the MAGIC research group in the Department for Earth Science and Engineering, but it's really the people in my team who do all the hard work. And I want to acknowledge those whose data I'm going to feature most today. And those are my two former PhD students, Karis Cook and Rachel Bertram. Rachel is somewhere in the audience. Emma Needham, who was an MSci student in our group, and David Wilson, who was a postdoc here for a long time and colleague. And they are the ones who produced some of the data I'm going to show you. But I also want to give some credit to two people without no research in our group could ever happen. And I'm particularly pleased that Katarina Kreisig is here tonight. Wave, Katarina. These people never get the credit. Katarina Kreisig and Barry Coles, our two lab managers. And then, last but not least, a long list of international collaborators. I started all of this work while I was a young postdoc at Columbia University in the US. There's been a lot of expeditions and people involved, and of course, a lot of funding agencies who made this work possible. So let's go on a journey, and go on a journey to my favorite continent down south, Antarctica. I want to start with talking a little bit about what it means to live in a changing world and what the warming climate is actually doing to the Antarctic ice sheets. I then want to keep it very short to talk a little bit about how we can look at the mud from the seafloor and the chemical fingerprint that mud holds to learn something about these ice sheets. And I hope I can explain to you how we do that. And then we're going to go on a proper journey. Most of you will only be used to be thinking about days, years, maybe a few decades. We're going to surf back in time for a few million years and see what we can learn from the past about the future of the Antarctic ice sheets. So I want to start with one of the iconic pictures we often see depicting how our planet is warming. We can see here global temperature anomalies for the years 2004 to 2014, and the red colors on this slide show areas which are warming, blue colors are areas which are cooling. And of course, at a first glance, you can see that most of the globe is red. But what you can also see is that it's not the same red everywhere. So global warming is not a uniform thing. The warming is actually more pronounced over the continents than it's over the oceans. As a consequence, then more pronounced in the northern hemisphere than the southern hemisphere. And it's more pronounced over the poles than it is close to the equator. The consequences of this are many, and I guess we start getting a bit of a taste of it now with heat waves, such as the one we had last year, flooding events, we just had one last week again. And the consequence I really want to focus on here is that of sea level rise. The seas are currently rising with 3.2 millimeters per year, and there are three main factors responsible for that. The first one is simply that warm water is expanding. That's about a third of it. The second one is that we have a lot of ice tied up in glaciers, mountain glaciers these days, and these mountain glaciers are retreating globally. You can see here a picture of the Quilcaya ice cap in Peru with a historical photograph from 1978. The picture is filled by a glacier in the forefront, and then in 2011, you can see the glacier is gone, and you can see a glacial lake. I could pull pictures like that from really places all over the world. But the last third of the sea level change is the one I want to address, and that is the one to do with the polar ice sheets we have sitting on Greenland and Antarctica. And as I call it here, that's really the rising giant in the sea level equation. We have today about 7 meters worth of sea level equivalent tied up on Greenland. That already sounds like a lot of water if you would melt it. But if you look to Antarctica, that's even almost an order of magnitude higher. So together, we have about 60 meters almost of sea level worth tied up in Antarctica, about 5 meters in the smaller Western Arctic part, and about 53 meters in the bigger Eastern Arctic part. If you just want to picture how much water that is, if you would melt all that ice, that would take the sea level to basically half the height of the London Eye here in London, or just below the clock of Big Ben. These are just two kind of pictures you can keep in your head. It's a lot of water. And of course, I'm not saying that that melting is imminent. Of course it's not. But we're living in London, and we're living not too far away from the sea. So it's really worth kind of thinking about this. And this is a view on our city, kind of Canary Wharf and the O2 Arena here from the east. And in the forefront, you can see the Thames Barrier. And the Thames Barrier is one of these brilliant pieces of engineering which was done in the 1980s, following a major flood in the 1950s, which occurred here in London. And it's there to keep our feet dry. So this is the blue hatched area on this slide is the area of the floodplains of the Thames if we wouldn't have the Thames Barrier, if they wouldn't close it from time to time when we have tide surges coming in. I'll leave this slide up there for a bit. I don't know where you are living, but I'm living right here in Fulham. So it's something we really have to think about with rising seas. The barrier was not built to withstand half a meter or a meter of sea level rise. And the picture is taken from the Environmental Agency T2100 plan, which looked at exactly that issue and decided with major sea level rise, we have to be thinking about upgrading the barrier or even building a barrier further closer to the sea or even a barrage. So this is what we should care as well. And with that, I want to go back to our ice sheets. What does the picture look like? What are the ice sheets doing today? So this is a figure taken from the IPCC report from 2013. And you can see Greenland and Antarctica and changes in ice loss in red and ice gain in blue on here. The clear picture you can take from that is that pretty much all of Greenland is losing mass. There's bits close to the summit which are still accumulating snow, but mainly Greenland is melting and it's losing ice all around. In Antarctica, that picture looks rather different. So we have a kind of two-sided story here. We have the Western Arctic, and particularly the area labeled here as the Amundsen Sea, where ice loss is happening very rapidly, shown by the red colors. But then we have kind of the big Eastern Arctic ice sheet, which looks rather stable on this figure. And for a long time, people really thought it was rather stable as well. However, newer data done since the IPCC report show clearly that we not only have mass loss happening in the western part of Antarctica, but that Antarctica as a whole really is losing mass, and that there has been a threefold increase in that mass loss since 1992. So let's spend a minute thinking about why West and Eastern Antarctica look so different. In this cartoon, you can see on the right-hand side an ice sheet that sits on bedrock that's elevated above sea level. That's what we call a continental-based ice sheet. And East Antarctica as a whole is considered kind of a continental-based ice sheet. Such an ice sheet can only melt top-down, so you have to warm it from the atmosphere, and there's a strong history in doing that, so it's very difficult. On the other side, on the left here, and that's more what West Antarctica looks like. It's a marine-based ice sheet where the ice rests on bedrock suppressed below sea level. And what that means is if you warm the ocean, or if you kind of upwell warmer waters from the ocean onto the shelves of the Western Arctic ice sheet, you take away the buttressing ice shelves and kind of accelerate the whole system and can actually eventually destabilize it if it's sloping inland as well. So that's the major difference between West and East Antarctica. But I'm putting up here now in the corner a map which shows you the bed elevations, or the topography of the continent of Antarctica, if you remove all the kilometers of ice sitting on top of it today. And what you can see here in blue is the areas which would still be below sea level. So clearly, most of West Antarctica is still below sea level, and that would give us about 3.5 meters of sea level equivalent. But what you also see is that there's large areas in East Antarctica, and I highlight them here to make it a bit easier, which are also in blue colors. They are also subglacial basins, and together, these basins hold about 90 meters of sea level equivalent. So that's about 6 times the amount we can melt from West Antarctica. And the major question is really, can these areas destabilize as well? We don't see them melting very quickly today, but there's first signs that they may be doing. So another nice picture from one of my expeditions. I'm very grateful that I get to go down south quite a bit. This was on the German icebreaker Polarstern here, which is actually not a tiny ship, but it looks tiny next to this guy here, and that's not the front of the ice sheet. It's actually an iceberg. So that's the size of icebergs which are carving out of the actively mass-losing areas in the Amundsen Sea today. So we know that Antarctica is losing mass. It's melting. We know that many people live close to the sea, and we are definitely not the ones most vulnerable. There's other cities much closer to the sea. There's low-lying island states, and many other reasons which have a lot more reason to concern than we have. So we really need to understand what lies ahead of us. And just looking at the observational data from satellites is not doing the job. We can't really get a feeling for what happens under 1, 2, or 3 degrees of warming. So this is the moment where it becomes rather handy to be a geologist, because we are not afraid of time in all kinds of dimensions. We can look back in time, study the record of the past. Our Earth has seen all kinds of climate states, and use that to hopefully help us inform what may happen in the future. And this is one of these kind of diagrams we produce as paleoclimate people. Time on the x-axis here now goes from 60 million years in the past. Don't be afraid of it, it's just a number. Kind of to the present day. And then these shaded areas at the end there are projections going into the future. So you can see over that 60 million year history, there's lots of different temperatures we can observe. So let's play the worst case scenario. Let's take the red kind of future projection, worst case scenario, and extend that all the way back and see where it hits our paleoclimate data. Well, it does so all the way back here, in a time period called the Eocene. That's when we had no ice on the planet. We had crocodiles living in the Arctic, palm trees in Antarctica. Very different planet, probably a planet we don't want to live on. That's kind of taking all that ice from Antarctica and filling it up to half the London Eye, as I said. So let's hope that humanity is sane enough to not drive us anywhere close to that direction. I put up a blue box here, which is the current pledges and policies. So that's what governments around the world at the moment, following the Paris Agreement, have declared they want to aim for. And that gets us to a warming of 3 to 3.3 degrees. So that is quite a bit lower than the red line, and it gets us to this blue line here. And that hits kind of our paleo curve in a time period called the Pliocene. So the Pliocene, the older part of it, was 2 to 3.5 degrees warmer than it is today. CO2 in the atmosphere was very similar to today, about 400 ppm. And the question now is, what did sea level do during that time? Well, our best estimates for sea level during the Pliocene are quite kind of a range, because it's really hard to nail that sea level that far back in time, but probably somewhere between 10 and 30 meters higher than what we have today. So if we do the numbers game, I told you Greenland is about 7 meters worth of sea level equivalent. West Antarctica, 3 to 5 meters. So anything above, let's say, 12 meters definitely needs contributions from East Antarctica. So there's evidence from the geological record that we really should be looking more at East Antarctica, and that's what I want to do today. So let's have a look at how I want to do this. If I have a choice in how I do research, the first thing I always do is go on a ship. So this is my favorite ship. I don't get to do this every time, but once in a while. This is the JOIDES Resolution, a drill ship used by the international community, originally built for the oil industry, used for scientific purposes since the 1980s, for all kinds of earth science questions. You can see it's quite a long ship with a high derrick, and in the middle, it has what we call a moon pool, which is nothing else than just a hole in the ship. Sounds wrong, but it works. It somehow doesn't sink. And we can lower a drill pipe through that hole, through thousands of meters of waters to the seafloor, and then drill a couple of kilometers into the seafloor. So that's how we get our sediments. Because if you think about the seafloor, it's like a cake where the top layer is the youngest bit, and the further you go down in your cake, the older your layers get. So this is what keeps us a record of the climate of the past. We normally then reconstruct sea level from these little guys. These are shells of marine organisms called foraminifera, and measuring their chemistry, we can figure something out about past temperatures and past sea level. The bummer around Antarctica, though, is we don't really find them. They don't really like living there, and our sediments look more like this, brown and gray muds. So we need some methods which can get us beyond this and learn something from the mud. And luckily, in my research group, we're quite happy with seeing lots of muds, because mud and sand from the seafloor is what keeps a really good record of the erosion of the continent. So here's a little cartoon where I kind of colored in different bits of rocks cropping out in different colors. And if you grind down these rocks from the continents and deliver them to the ocean, there's two main ways how you can do that. You can either do it by ice rafting. You can see the red and green bits here go into this iceberg. The gray bits go into this iceberg. And then the icebergs eventually melt, rain out their debris. And then back in time, you can find these layers of ice-rafted debris. And they carry a fingerprint in terms of their chemistry, which is absolutely comparable to the rocks on the continent. So if you figure out what you have in your sediment core, you know where on the continent it was coming from. We also do that with the fine washout, which comes kind of in plumes of meltwater from underneath the ice sheet. And that's what I mainly want to talk about today, because it's the fingerprint of this kind of fine outwash material, which really tells us where the eroding ice margin was sitting at a time back in time. And that's how we can then not just say what material it is, but actually where it was eroded. So that way we learn about the ice sheet. A very quick slide. The first thing we do, we kind of behave like we're kids again, play in the sandpit, have some sieves, and do some sieving. We separate out coarse fractions and fine fractions of the material, and then we throw kind of all kinds of geochemical methods we have at it. And I'm not going to bore you with any of the details. There's lots of different elements on the periodic table we can use in isotope systems. The ones I want to talk about today are mainly strontium and neodymium isotopes in the fine fraction, but it doesn't matter what they exactly are. You can just think about them as chemical fingerprints. In order to do this work, you however need really fancy laboratories. And this is my slide to say a cheer to all the people from the MAGIC group who are here tonight, but to also thank college, thank the faculty, and thank our department for the continued support we get for our MAGIC research facility, which is 70 square meters of clean room space, and it hosts 3 really top-notch mass spectrometers. If you haven't seen the facilities, shoot me an email. They're in the basement of the Royal School of Mines. Always happy to take people on tours. So, what do we do then? This is just kind of a quick slide to explain to you this fingerprinting method I referred to. So in the example of neodymium isotopes, it's a radioactive clock system, so there's a parent isotopes, the 147 samarium here, which decays to a daughter, the 143 neodymium, and we normalize that to a stable isotope of the same system, and it basically means that the age and the composition of the rocks on the continent all deliver characteristic fingerprints. That's why we have a fingerprint here. So it's like an environmental tracer, if you want so. And it works really well around Antarctica because we have a very varied geology around the continent. Antarctica has bits which go back to the early days of our planet Earth, billions of years, to active volcanoes, which are still there now. So this is kind of our playground for isotope geochemists to learn something about ice sheets. But let's go and look at some data now. What can we learn about this Pliocene time period when it was 2 to 4 degrees warmer than today? Well, first step, as I said, go on a ship. So in 2010, I had the pleasure to go for the first time on the JOIDES Resolution on an expedition down to Eastern Arctica here. We sailed out of New Zealand down and then back to Australia. There's always kind of around 30 scientists on board. We work 12-hour shifts, 24/7 for 9 weeks. It's a lot of fun, but it's also hard work. By the end of these expeditions, you've normally found a lot of new friends and colleagues. You also know who you don't ever want to sail with again. But what is for sure is you come off the ship with some material no human being has ever seen before. You get these sediments which are millions of years old, or thousands of years old, which nobody's ever seen before, which is truly cool. So you just kind of can work on this material for some period. Nobody else can. So that's part of the reason why you really want to go out there. The one reason why you may not want to go out is if you get seasick. That probably only applies to the Southern Ocean in that extent, but the Southern Ocean is known for its high waves. There's really strong winds sweeping across, and this is standing on the back of the JOIDES Resolution with a wave. I'm not sure whether any of my colleagues were still standing at that moment. A lot of people go green in their face and become a bit ill, but I luckily don't get seasick, so I love going back. It's just really fantastic. But if you survive it, there's always the light at the end of the tunnel. Once you get south of that strong wind belt, that's what it can look like. So this is the closest we got to Antarctica on that particular expedition. Here's the silver lining of the Eastern Arctic ice sheet in the background, some grounded icebergs in the forefront, and that's what sunset looked like. I was working on the noon to midnight shift, so I never got to see sunrise. But you've seen this picture already. That's what it looked like during daytime, which was not too shabby either. When you're down there, this is a photo which tells you it's time to go home. So around Antarctica, the sea ice-free periods are only 2 to 3 months in most of the regions where you work. So if you really want to get close to the continent, you have a small time window when you can do that work. And this is what the beginning of sea ice looks like. So if you're on a ship like the JOIDES Resolution, which is not made for withstanding the ice, it's time to get out. And that's what we did. And here's some of the examples of the sediments we came back with. We drilled sediments from the greenhouse world, the Eocene world, and we actually found pollen of palm trees and relatives of the baobab trees in exactly these sediments here. So we know there was subtropical vegetation in Antarctica some 50 million years ago. We also drilled records of seasonally laminated Holocenes, or records which are just a few thousand years old, which will give us a lot of insights into the interaction of the ocean and the atmosphere in that particular region. And here again is the picture, the least spectacular looking one, I have to say, of the Pliocene muds. So that's what I want to talk about now. And don't worry, there's not going to be many diagrams with wiggly lines, but I had to leave that one in because that was the first kind of paper we, as a group, produced from this expedition led by my former PhD student, Karis Cook. So we're looking at a record from 5 million years ago to 3 million years ago. And you can ignore all the wiggly lines and just kind of concentrate on the pink and white bands. These pink bands are in times when you have these yellow blocks here, and these yellow blocks are sediments of a certain composition. They're diatom-rich silty clays, so they're microorganisms which live preferentially during this time, which show that there's higher productivity in the ocean, which means less sea ice and warmer conditions. So the pink bands are warmer times during the Pliocene. The grayish-blue bands then are colder times. So in the Pliocene, it was sometimes a bit warmer, sometimes a bit colder, like in all other times in Earth's history. So we measured some isotope records, and they are shown on the right-hand side here now. And I put in some stippled lines because, again, we don't need to worry about any of the detail. What you can see that these chemical fingerprints we now measured on the bits of rock found in our sediments, they kind of co-vary with what the composition of the sediment does and with kind of what productivity does and a lot of other things in this core. So what do these systematic variations actually mean? Well, that's the point where we have to do our homework, and that's, again, where it comes in handy to be a geologist, because we have to actually look at the continent now and at the different geological formations we find on land. And that's what you have in this map here. So our drill site is here, so north is going up to the ceiling. Here's our deep Wilkes subglacial basin, and you can see in 4 different colors, 4 different rock formations, if you want so. If we plot them up in our isotope versus isotope plot, again, it's neodymium and strontium isotopes, but the details don't matter there. We could have taken some other traces as well. We get what is kind of the dream of every isotope geochemist, 4 nicely distinct bubbles. So that means you can nicely trace the different units and figure out what they are. Plotting on top now our sediments, we figure out that the black diamonds here are our sediments from the colder times in the Pliocene. So they plot in this blue bubble. The sediments from the warmer time in the Pliocene plot outside that blue bubble, and they plot towards that green bubble. So again, we can see that sediments from warmer and colder times seem to come from different areas. You may get a bit bored now and say, where's she going with all of this? This is like nerdy kind of geochemistry and geology. No, it's not. We're getting back to exactly what it means now. So we're going to zoom into this area up here and going to look at what the mechanistic explanation of that data is. So during the colder times in the Pliocene, we mainly eroded material from this glacier here, the Ninnis Glacier, which is connected inland to a deep basin. And that signature, that blue signature, which is Paleozoic granites, is what we find during the cold Pliocene, but we also find it today on the shelves of Antarctica. So the colder times in the Pliocene looked a bit like today does. If we go now to the warmer times in the Pliocene, the picture is drastically different. So what we see now at our drill site is this green signature. So that's some particular basalts which are found in the area. And if we go back to the continent, there's very little coastal outcrops telling us anything about this lithology. But we know from geophysicists flying with airplanes over the ice sheet and taking measurements of the magnetic structure, the gravity and many other things of the rocks underneath the ice, that these basals probably fill up a big part of the interior of that basin. So that's what the green hatched area is. And that's what made us conclude what we're seeing here is actually evidence for a retreated ice margin inland, which then funnels out all these fine-grained sediments to our side here. So during the Pliocene, we had a dynamic ice margin with repeated ice advance and retreat. And you may ask rightly now the question, well, why does that matter so much? It actually mattered a lot at the time we published it 6 years ago now, because the picture on the top left here was what our general understanding about the Pliocene and the Eastern Arctic ice sheet was from models. That was the only way, if you don't have direct data evidence, how you can understand the system, you look at models. And the models thought in the Pliocene, West Antarctica had collapsed, but they didn't really see anything in Eastern Arctica, which really did not match with our data. So the modelers went back, did some more kind of searching, did some more work, did some observations in modern glacial environments, and came up with 2 additional kind of physical procedures they didn't really have implemented, which were those of cliff failures. When you grow large ice cliffs over the waterline, these can become unstable and collapse, and hydrofractures. So from cracks, kind of you can collapse your ice sheet as well. And once you kind of include these 2 guys, that's what I call here the new Pliocene. That's what their new model runs look like. And you can see now West Antarctica is still collapsed, but now there's a big dent in our area here as well, the Wick subglacial basin. And you can actually see now dents in other parts of subglacial basins in Eastern Arctica as well. So that particular result came out of their models from 2 degrees of warming over 5,000 years. So we thought, can we do anything to contribute to that? And I see Rachel smiling, because Rachel surely could. So she went back to our same sediments and measured at much higher resolution than we did before to get to the rate of change. How quick do these events actually happen? And again, lots of wiggly lines. You don't have to understand the detail, but she measured, like at the bottom here, 2 different isotope systems in 2 different intervals in the Pliocene. And what she came up with is that the rate of change was a few thousand years as well in her sediments. Very similar to what the modelers found in their data. But she could do a bit more with her data as well and actually think about, well, what's actually the sequence when you kind of retreat an ice margin, when you stop melting that ice? What does that do? Well, the first thing we see in our data records is you get some carving of these big icebergs, and they deposit a lot of this ice-rafted debris at the seafloor. The next step you get then is you retreat the sea ice, which cranks up the productivity of the organisms living in the surface ocean, and at the same time, you retreat your ice margin. And that's exactly what she found as well. So that's good. We have kind of data and models giving us similar answers here now. And I want to leave the Pliocene right there, because we all know that in 2015, we had the Paris Agreement, and what kind of nations around the world agreed on is to try to keep global warming below 2 degrees, and if possible, below 1.5 degrees. So hopefully, we don't have to worry about our Pliocene example. We have to worry about something which is less warming. And I just want to take you for the remainder of the talk into a little example of what times look like where the warming was less. So let's take a lower stippled line here now and see what we can find in the Paleo record. And I circled here 2 intervals in a time period called the Pleistocene, which are the last interglacial, MIS5 as we call it, some 125,000 years ago, which was 1 to 2 degrees warmer than pre-industrial, and MIS11, 400,000 years ago, 1.5 to 2 degrees warmer. So what did sea level look like during these times? A lot more recent in time history. We have a lot more records to look at now. We know actually sea level quite a bit better than we do for the Pliocene. During the last interglacial MS5, sea level was probably 6 to 9 meters higher to today. During MS11, it was probably 6 to 13 meters higher than today. So again, if we do our math, in this case, we know that Greenland can't have been completely gone, at least for the last interglacial, because we have ice core data from Greenland. So we know there was still some ice on the continent. So we probably only get a couple, maybe a few meters out of Greenland. Well, West Antarctica, we still don't really have data, but everybody thinks that probably lost some ice. So there's still room for potentially having an East Antarctic contribution. And to embarrass the next person in the audience, now David comes in, and this is work David Wilson did together with Emma Needham. What they did is they went back to this core site, still the same site from that one expedition I went on, and produced now a high-resolution record here for the last 500,000 years. Plotted in red is our isotope record, and in green is this record which tells us about ocean productivity, so how happy the bugs are and how warm it is. And you can see a really stunning correlation there. It's actually something we totally did not expect, and I want to make the point why you always have to do some blue sky science. This is not what we predicted. We predicted a flat line, but here we go. A stunning correlation. And if we tease these two apart now, the only way we can interpret them is because they really look like the Pliocene, is that we had ice loss during these late Pleistocene interglacials as well. So the low-lying Wilkes subglacial basin was probably losing mass as well. As I said, it's more recent in time, so we can compare it to a lot of other wiggly lines. The ones at the bottom now are about regional temperature. And what David really found is that what's critical for the retreat of the ice or the loss of the ice in these areas is not the absolute temperature, it's the amount of time the system stays above a certain temperature threshold. So in this case, it was a couple of thousand years above 2 degrees, which led to significant ice retreat. And if you compare it to the top curve here, which is a global sea level curve, you just have to say that our red isotope curve we have here looks rather similar. So I think there's no way around saying that there is some East Antarctic contribution in these late Pleistocene interglacials. So to summarize, the low-lying areas of the Eastern Arctic ice sheet, an ice sheet we saw traditionally of as a very stable part of the Antarctic ice sheet, contributed to sea level rise. They did so during the warm Pliocene when it was 2 to 4 degrees warmer, but they also did so during the late Pleistocene when it was only 1 to 2 degrees warmer. So there's probably a lot more reasons we should look at these areas now. And the one take-home message I want to kind of bring in this summary slide is that the paleoclimate data really tell us that there's already a lot more sea level rise in the pipeline. So we have temperature on the x-axis here, sea level rise on the y-axis, and the boxes are the different time periods I discussed. The Pleistocene ones in green, and then the Pliocene in red. And you can see how every degree of warming leads to more and more sea level rise. The Earth system is a very slow system, and I was a couple of months ago at a press briefing with Martin Seagaard. I don't know whether he's here, but he brought up, there he is, a very good analogy, which was when you're at home and you want to bake a cake and you turn on your oven. You set the oven to 200 degrees. What happens now? Of course, the oven doesn't jump immediately to 200 degrees, right? It takes some time to get there. And that's exactly how the climate system functions. We pump CO2 in the atmosphere. It takes some time for warming to materialize. Once we have the warming, the sea levels are yet a bit, or the ice sheets are yet a little bit more sluggish. So it takes some time till the ice sheets react to that warming. So there's a delay in the system, and with everything we do right now, we have to basically think about the future commitments we are making today. And that's why kind of just looking at lines like this one here at the bottom with the IPCC projections for the year 2100 are sometimes a bit misleading. whether we have 0.5 meter or 1 meter sea level rise by the end of this century is surely very important for immediate adaptation. But when we think about climate mitigation and what we should do, we really should keep in mind these long-term commitments as well. So what's next? Well, clearly, we have our work cut out in the Antarctic community. I just talked for a long time about one single drill core in one location. So what I did last year is I went back on the JOIDES resolution on an expedition to the Ross Sea, and together with 2 other expeditions which happened this year on the same ship, we now have a program, and that really came out of a community effort from the Antarctic community to say we need to know more about the West Antarctic ice sheet, to have basically 3 drill locations to piece together a better picture of the West Antarctic ice sheet, which from the data side, the paleo data side, we really don't have right now. But after everything I told you, I think it won't come as a surprise that what we also need to do is we need to look at East Antarctica. Before I get there, another point to stress, there's a joint US-UK program focusing on the Thwaites Glacier, which is one of the really fast melting glaciers in the Amundsen Sea. And we just submitted a drill proposal to go through the ice into a sediment basin under the ice and see what the sediments in there look like. But to get back to my point, East Antarctica, the Aurora and the Recovery subglacial basin, there's very little we know about this in terms of data, so this should definitely be future targets. So after the failed climate summit in Copenhagen, this cartoon kind of made the rounds, and I used it for a number of years at the end of my talks. So there's somebody sitting in the audience saying here, what if it's a big hoax and we create a better world for nothing? Looking at this long list of benefits from decarbonizing our society, green jobs, renewables, clean water, healthier children, etc. And it's quite nice that that whole narrative seemed to have changed. We had the Paris Agreement in 2015. We had the 1.5 degree warming report coming out last year. And last but not least, I think the heat wave we had in this country last year helped quite a bit as well, because in the public media, you can see now more recommendations to use the words climate crisis and climate emergency instead of climate change. And our government declared months ago climate emergency. But of course, this is all words. What we really need is action. And I think as a climate researcher, what gives me real hope is seeing the young people on the streets week after week right now, inspired by the wonderful Greta Thunberg. And last week, Jo Haig met with the Prime Minister, and she agreed to the recommendation of the Climate Change Committee for a zero carbon goal for the year 2050, which I think is really important. And I want to finish with a quote from Sir Brian Hoskins on that date. We led the world in the first industrial revolution based on fossil fuels. Now we are taking up the challenge of leading in the next green industrial revolution. And I think there's few places which are better placed than Imperial College to actually take on that challenge. So let's do it all together. Let's give the kids on the streets some hope and a fighting chance to keep our ice sheets where they are right now. Thank you.
Well, thank you, Tina. That was beautifully to time as well. So that allows time for some questions, and I hope there will be plenty of those. So please, could you raise your hands if you'd like to ask a question? Yes, there's one there just close to you, yes.
Thank you for the talk. It's very interesting, but I think you proved that most of the change has been geological rather than human-caused. And one thing you haven't mentioned about East Antarctica is whether there's a temperature change in the interior of the Earth, which may be causing the interface between the ice sheet and the surface to cause that flow into the sea where the ice sheets cantilever off, creating an increase in sea levels. But has Antarctica moved in 5 million years? When Pangaea started to break
Okay,
up.
there's a few questions there. Is there internal heat source?
How has the latitude changed from
Okay,
5 million years
right,
to
and the
now?
latitude, yep.
Happy to take that on. So the latitude of the Antarctic continent hasn't changed in 300 million years. So it's been at the same place over the South Pole for much, much longer than the time periods I've been talking about here. In terms of the heat source, there is always internal heat sources, of course. There's bits where the Earth's crust is thinner and more heat comes to the surface than others. Today, that actually mainly is observed around West Antarctica, and that may be contributing to some of the faster melting we see in the Amundsen Sea area. East Antarctica has a very thick continental crust underneath it. So in those areas, that is rather unlikely to play a role.
Okay, do we have some other questions around? Please, at the back there.
Oh, thank you for a very interesting talk. My concern is on the rate of change, and you've shown the changes over sort of 500 million years, but and clearly the climate has changed over that time quite dramatically. But the concern today is just how quickly it's changing, literally in the last sort of 100, 150 years. And I'm wondering if you could just put that into some sort of context over, you know, the last 150 years as against the last sort of 500 million years, if that's possible.
Yeah, that is possible. We try to look at that quite a bit because everybody is aware that the rate of change is really what's going to define how worried we have to be about any of this ice melting in the near future. Long term, there's no question where the system is going, but for the near future, that's a different question. From the data I've shown you, the resolution is not quite there. So we can see in the past these changes happened over a couple of thousand years. But that is really a maximum estimate. Whether in those couple of thousand years there was one event which basically made the system spring to a different point of stability within, say, a few decades or a few hundred years, we can't quite exclude that right now. And that's where there's a lot of focused research going on to try to understand the mechanics of how the ice reacts to the warming a lot better to try to nail that down. But in the geological past, there have been some events which are rather quick on our timescale, but as you rightly say, we're doing an experiment right now which has no precedent. The carbon dioxide in the atmosphere has changed so much over the last 150 years, which was not a case in any of these examples I've seen. And as I said, the system needs some time to respond to that, but we need to figure out where the tipping points are. When does it flip? And we don't quite know that.
Yes, that brings up the stability. I mean, there's some thought that with Greenland that there could be a level of warming where it's almost irreversible, that you lose the ice sheet. Is there any sort of thoughts around that?
There's definitely thoughts around that as well, and particularly in the West Antarctic at the moment, the Amundsen Sea area. This is why there's a lot of effort going into understanding the Thwaites Glacier better, because that is one of these kind of glacial catchments which sits on bedrock, which is sloping inland. And there is concern that if you lose the pinning point where the ice sits on the bedrock, the whole system could go. And once you're beyond it, you can't really stop it anymore. And there's some suggestions that may already happen, but as I said, there's a lot of research going on trying to really nail that down.
Yes, there's one over there, yes.
Yes, thank you, Tina. Wonderful lecture. I was wondering if there is a role for the ocean in when you think about the evolution of Antarctica ice sheet, because surrounded by the Southern Ocean.
Thanks, Arno. Absolutely, the ocean matters in everything. As you know, I'm in the Western Arctic areas at the moment. The Amundsen Sea, it's the upwelling of warm circumpolar waters on the shelves, which is actually the main agent causing this rapid ice retreat. Around East Antarctica, the area where I've been talking about, the Wilkes subglacial basin, we don't at the moment have the observational data to prove whether there's warm water upwelling on the shelf, but we also don't see a lot of retreat today from the satellite data. Another area in East Antarctica, the Totten Glacier, you actually see these incursions of the warm water onto the shelf, and that's also where melting rates are accelerating. So absolutely, the ocean plays a big role in all of this, and I think the ultimate understanding has to come from coupled ocean ice kind of models, really.
Yes, we have a question here.
So, I wondered about statistical methods that you use to analyze your temperature data. Whether you tested in any form the predictive value, are they predictive, it would be apparent, or can you sort of verify in some sense goodness of fit tests or something like that?
Yes, in general, so my group is not the group who's doing temperature data, but what you asked applies to any sort of data set, right? So we all have to be rigorous with the ways how we collect our data. So in our case, looking at the chemical fingerprint of sediments, we always compare it to first for the modern day, before we do any work back in time, because in the modern day, we can sample it, we can measure it, and we can compare it directly to what we find. And then, once we have proven relationships, we take that back in time. If the relationships are shaky, we stay away from that tracer.
Right, there's one in the middle there. Yes, to the lady there.
Thank you very much, Tina, for your talk. So my question is, you showed 3 events in Pleistocene where the temperature rose very quickly, but also decreased very quickly. So do we know why the temperature went down after these 3 MI events?
That's a good question, and probably one I can't answer comprehensively. The temperature kind of rise and fall in these late Pleistocene events is the first order signal you see in there is Milankovitch forcing. So you get these interglacials every 100,000 years. So it has to do with the kind of orbit of the Earth around the sun and the different kind of climate cyclicities we get from that. So that's a first order control. But then there's a lot of feedbacks in the system as well. So you wouldn't draw down the CO2 to glacial levels where it was and bring it up in interglacials again if it would just be that. So there is a big role for the ocean again. There's ocean biogeochemistry, which has a feedback. There's a role for sea ice and many other factors which kind of govern these general cycles in the late Pleistocene.
Right, is there, yes, one question there. Sorry, it's over the other side from you, but there's a gentleman over on the other side then.
With the, say, the increase of 9 meters for the Antarctic ice shelf, the increase in the water column, does that happen evenly throughout the globe, or is the water increase, say, confined to the southern hemisphere?
That's another excellent question. So no, it doesn't. So we talk a lot about global mean sea level, just as a way of kind of giving a number people can picture. But as a matter of fact, when you melt, let it be Antarctica or Greenland as well, there's what we call a kind of melting fingerprint on the solid Earth of that, which is something we call glacial isostatic adjustment. It's just like a really complicated kind of terminology. But it basically means, for example, let's stay closer to home. When you melt the Greenland ice sheet, you take mass away from the continent and put that mass in the ocean. And what that leads to, actually, right next to the continent where you're melting that ice, is, first of all, a sea level fall and not a sea level rise. And we're here in the UK, actually, at what we call the forebulge of the solid Earth. So the Earth kind of comes up a bit because that mass has been taken away from it. So we here probably wouldn't see the sea level fingerprint from Greenland. But if you go to the equator, that's kind of where you would see it to the full extent. So the people who reconstruct these sea level records back in time need to very carefully choose their locations where they look, because it's not globally the same. So it's a very good point.
Okay, I think we might be drawing to an end unless there's one more question there. Yes, one more, and this will be the last one. Okay. Sorry, keep you fit.
We know, of course, that the sun must have a great effect on the Earth's climate. Have you done any work on the correlation between solar activity and prevailing temperatures on the Earth over the last few million years, if possible?
It's certainly possible to do that work. I personally don't do that work, but I listen carefully to my colleagues who do. And there is very clear signs that the climate fluctuations we see are independent of the fluctuations we get from the pure solar radiation.
Okay, I think we better draw proceedings to an end now, and I'll ask Professor Mark Ray Camper to give a vote of thanks.
Sit down.
Good evening. It's my honor to thank Tina for the fantastic talk that she's just delivered to us and all the insights we've gained through your talk about how we can learn about the future climate of our planet by looking into the past. Now, considering that the Earth is, according to your talk, moving into a potentially precarious situation, it sometimes surprises me how little worried we seem to be about the future that we're taking. I don't know. Perhaps it's just our generation is just taking it too easy. It's not worried enough, or our policymakers are not worried enough. And so, in that respect, I really share that hope that you put into the next generation that seem to have more conviction, seem to be more worried about the possible consequences, about the possible road that our planet is taking, and are willing to make compromises also to go toward a different planet, to make sure that we don't don't raise our sea level by 5 or 10 meters over time. So, this next generation, I put a lot of hope in that, and I just trust that doesn't mean that my own kids won't be missing school every other Friday or every Friday to impress these thoughts onto the politicians in Westminster. And just one more thought I want to steer across before I show you where the reception is that if you were a keen listener of Tina's talk, you will have realized that it involves a lot of collaboration, research collaborations, working together with a lot of other people, and this means working with people both for Tina, working with people from her field and working with people from different fields, and working with people at Imperial and in the UK, and working people in Europe and worldwide. And no, don't worry, I'm not going to take you down the Brexit route. I don't want to talk more about that, even though there are some possible consequences, obviously, for collaborative research. What I more want to really emphasize is that Tina really excels, really drives, really thrives in such collaborative research. And that's one of the, together with her enthusiasm, is one of her big scientific strengths. And essentially, I'd say Tina is really a role model for doing collaborative research. I mean, she knows how to make it successful as a combination of it being scientifically fruitful and personally rewarding. And she does that really well. And as a consequence, I mean, she has scientific friends all over the place, all over the world, but also lots of them here at Imperial. I'm one of those. I mean, I've worked together with Tina in days that go beyond the time here at Imperial for almost 20 years. And I can say I could wish no better colleague than to have her as a colleague. It couldn't be any better. But there's plenty of other people here in the audience, sitting up there, for example, her PhD students, former postdocs, colleagues, who would probably say exactly the same thing that I just mentioned here now. With this in mind, I would like to hope the audience shows her appreciation to Tina, not only for the excellent presentation that she gave, and then for those applicable also for her being a super colleague. Thank you, Tina.
We have a reception now.